The membrane of an egg is semi-permeable and holds a high concentration of dissolved protein. When the egg is in pure water, osmotic pressure causes water to flow into the egg and it swells. In highly concentrated sugar solution, the solute concentration is higher in the sugar water than in the egg. Now osmotic pressure causes water to flow out of the egg.
The fourth colligative property that we haven't talked about is osmosis. And osmosis is the function of a solution. It creates an osmotic pressure, all right? And the pressure is very, very interesting. So going back to the original idea at the beginning of this lecture, you can take an egg, place it in acetic acid, which is vinegar, and the hard shell goes away. It dissolves. Then you've got just the egg yolk, all right? And if you have the egg yolk in pure water, the yolk gets really big. So you can see in the picture there in the middle, the yolk is much bigger than the egg that it came from, if you will, or the average egg. The water makes the egg expand. On the other hand, if you put that egg in corn syrup, you can see that the yolk shrinks down quite a bit. So we're seeing here the effect, and osmosis is the effect of the solvent in the solution. It's actually creating a force. It makes the egg get bigger when it's pure water, and it makes the egg get a lot smaller when it's in corn syrup. So let's talk about what the heck osmosis or osmotic pressure is all about. In osmosis, you think about osmosis as there's like a solution on one side and pure solvent on the other side. And there is a semi-permeable membrane that separates the two. And the semi-permeable membrane usually allows solvent to go back and forth, but the solute on the solution side has to stay there. All right? So the semi-permeable membrane just allows solvent to go back and forth, but the solute is stuck on the left-hand side of that picture. Solvent molecules move from the pure solvent to the solution. It's almost like they're attempting to make both the solvent and the solution have the same concentration of solute. So what happens is your solution will start at a molarity. Let's say it's 1 molar, all right? And you put it in an osmosis thing like this one. The solvent rushes to the side of the solution, and your 1 molar value goes down. Maybe it goes down to 0.1 or even less. This is actually an effect of something called entropy. Entropy is a really cool subject. I love talking about entropy, but we have to wait on talking about entropy until Chemistry 223. It's very, very cool. But for right now, just realize that there's a reason why solvent goes to the solution. It's trying to make the concentration of the solute in the solution go down, be more like the solvent, if you will. It has to do with entropy, but I have to leave that right there. I can't talk about it, even though I'm like, it's really driving me crazy to not talk about it, but you can look it up online if you can't wait to Chem 223.
When a solution of higher concentration and a solution of lower concentration are separated by a semi-permeable membrane, one through which solvent molecules can pass but through which solute particles cannot, solvent molecules will pass through the membrane from the side containing the more dilute solution to the side containing the more concentrated solution. This process is called osmosis. Solvent molecules actually move through the membrane in both directions, but because the concentration of the solvent is higher on the right, solvent molecules on the right collide with the membrane more frequently than on the left, resulting in a net flow of solvent from right to left.
As the solvent, which can get through the membrane, passes to the side of the solution, and by the way, the solute molecules are usually bigger because they're hydrated or something like that, so they can't get through the membrane. But anyway, the solvent rushing to the other side actually creates a pressure, and it can push the column up. In the little YouTube right there, you can see that the orange side is like pushed up a little bit, and the blue side goes down. In the picture on the left-hand side, you've got a semi-permeable membrane, and the water is essentially rushing into the membrane, and it pushes the water column, or the solvent column, I guess I should say, up. And the height of the column can literally be measured in millimeters of mercury, just like we saw the regular pressure does. So these pressures are real. They can be measured with manometers and stuff like that, or you can actually measure it with a ruler, as in these cases, to figure out how much force osmosis is producing. And again, it's the effect of the solvent going to solution solution, all right? Solvent is rushing to the side of the solution, trying to make the concentration go down. Osmotic pressure gets the symbol capital pi right there. Now, pi is the same symbol that's used in math, the 3.14 number, but this is a totally different pi. This is the pressure of the solvent in a solution. So I think the reason why they use pi is that P is usually the symbol for gas pressure. Pi is like the equivalent Greek of P, but of course this is a solvent pressure. Anyway, osmotic pressure pi, which is the same as osmosis, osmotic pressure pi equals ICRT. Now, C is the concentration of the solution in moles per liter. I, if you need it, is the Van Hoff factor we talked about in the last section. So ionic compounds will have I's of 2, 3, stuff like that, but the organic covalent pieces will just have I's of 1. Now, R here is the good old gas constant R, 0.082057. It's the same R we used in PV equals nRT. That R is also used in osmotic pressure. And finally, T is the Kelvin temperature that you're going around. So you can actually calculate the osmotic pressure. It's going to be in atmospheres if you use this equation. And that osmotic pressure has a lot of interesting things you can do with it.
When a solution and a pure solvent are separated by a semi-permeable membrane, solvent can flow in both directions, but the solute cannot. Here, pure water moves into the solution, working to bring both the solution and pure water to the same concentration. This process, osmosis, continues until the flow of water across the membrane is balanced by the pressure exerted by the water column. A semi-permeable membrane blocks solute molecules, but allows solvent molecules to pass in both directions. The number of solvent molecules moving from the solution side to the pure solvent side is less than the number moving into the solution side, resulting in a net flow into the solution.
So both of these videos show again the effect of osmosis and how it creates an actual pressure, all right? The upper left one, when it pushed the column up, you can actually measure that pressure. It's usually measured in millimeters, centimeters, stuff like that. That can be translated to atmospheres. And then the one on the right I kind of like. It shows that semi-permeable membrane. There's like little tiny holes in the membrane. Solvent molecules go through, but the solutes don't, all right? And the solutes don't because they're either larger molar mass, or if they're ionic, then they're hydrated with water molecules, the ion dipole force. So the water molecules go back and forth, the ions stay on one side. And again, the tendency is for the pure solvent to rush to the side of the solutes. It creates kind of a smaller concentration. Concentrations go down. That's the effect of osmosis. And again, it can be measured as millimeters of mercury or atmospheres, all that kind of stuff. Here's a question which uses osmosis to calculate a molar mass. So just like we saw freezing point and boiling point, you can calculate a molar mass. You can calculate the molar mass through osmosis as well. It's usually used if you have a really big biomolecule. And in this example, we're going to calculate the molar mass of hemoglobin. Hemoglobin is one of these big organic molecules, which is just crazy. But anyway, I digress. Let's say we take 35 grams of hemoglobin and we make a liter of solution, and they measure the osmotic pressure pi to be 10 millimeters of mercury. So they put literally a ruler and it comes out to be 10 millimeters, and that's at 25 degrees Celsius. We can use this information to calculate the molar mass of the hemoglobin. Now, pi, the osmotic pressure, equals ICRT. I isn't going to be very useful to us here because hemoglobin is big and organic. You don't need I factors when it comes to organic things. You only need I factors with ionic compounds like sodium chloride. So I here will be just 1. We're first going to solve for the concentration, the moles per liter, and from that, because we have 1 liter, we can turn it into moles, and then grams per mole will give us the molar mass. So the first step here, we've got to get the osmotic pressure in atmospheres. 760 millimeters of mercury per atmosphere means 10 millimeters of mercury is 0.0132 atmospheres. That's the osmotic pressure pi. That's going to equal CRT. We can convert 25 Celsius into Kelvin to do C, or to do temperature, R is 0.082057, so the only thing we don't know then is C, the moles per liter of the solution. So if you do that, you get 5.40 times 10 to the minus 4 moles per liter. That's the molarity of this hemoglobin solution. Now, we have exactly 1 liter of solution, so that means that we have exactly 5.4 times 10 to the minus 4 moles. So if you take that 35 grams, divide it by the moles, you get the astonishingly big 64,800 grams per mole as the molar mass. Osmosis is used a lot in biochemistry as a technique to solve for the molar mass of these big biomolecules. It's really cool. Osmotic pressure works a little bit better than freezing point or boiling point changes. Osmotic pressure can be measured and calculated back. It's pretty cool. In the medical field, osmosis is critical. If you've ever had an operation done, they always hook you up to some kind of a bag to keep you hydrated. Well, if they hooked you up to pure water, there would be a problem, because pure water would go next to your cells, and the cell, if inside the cell, it's like a molarity, a concentration. And through osmosis, pure water would rush into your cells, making your cells get bigger and bigger, like the egg we saw earlier, right? And after, if you added enough water, the cells would explode, and that would be bad for your body. So the liquids they use are not just pure water. They're usually sodium chloride, potassium chloride, something like that. They have to be isotonic. They have to be the same concentration, roughly, as the cells in your body. So osmotic pressure is absolutely critical when it comes to the medical field. You must use isotonic solutions, or else your cells are going to freak out. Freak out in the real medical world, not a very science term, my apology, means that the cells will either go to hypotonic or hypotonic, all right? In a hypertonic, then what you means is the liquid molecules, the little blue molecules inside that cell, are going to all rush out, all right? And if they all rush out, the cell will shrink down. On the other hand, if you have pure water, then the water molecules on the far right are going to rush into the cell, make it bigger, that's going to be hypotonic. You want to have isotonic, where you have water molecules going into the cell and water molecules going out of the cell. And you can do that if the outside solution is about the same concentration as your cells. And there are ways to figure that out, stuff like that. Reverse osmosis is really helpful, and it's becoming more and more important, for better or worse. It's used to desalinate water, so you can take seawater, which people can't drink, pull the salt water, the salt part of the salt water out, and pure water comes in. Now, this is a really interesting kind of process, and it involves super high pressures. So if you add something like 30 atmospheres or more of pressure, all right, to a saltwater system like seawater, the high pressures actually push the solvent molecules out of the solution. That's really against what normally happens, but it does work. High pressure systems, you can get pure water out, and this will create pure drinkable water. And that's really important for places with water shortages. So in the Middle East, that was the first places I had ever heard that they were using this, but now they're using it in Florida and Los Angeles and lots of big metropolitan areas where water is a little bit of a privilege sometimes. This creates more drinkable water. It is a pretty high energy process because you need to have very high pressures to force the water molecules through. In the lower right-hand corner, there's a picture from a water salination plant. Each one of those tubes has a semi-permeable membrane in it. They have super high pressures. They push the water through. Then you have water for drinking, etc., etc.